Okay, so I am starting this session right now. This is my eighth take. Hopefully this works out. In the last one, I got a call from the school saying there was no classes until next week, and that got recorded. No, I did not. I had to redo the take. Anyway, we are looking at chemical kinetics. Remember the chapter is chapter 14. I'm going to go straight into it because I think, yeah, I'm just going to go straight into it before something else goes wrong. So right now, let me make sure I am recording though, just so that we don't have an issue there. I am recording, and then let me make sure my audio can be heard because that was an issue before. I am recording and my audio can be heard. Okay. So we're going straight into the lesson. Chemical kinetics is the study of the factors that affect the rate of chemical reactions, such as temperature. We will see later on there's more than just one factor, but for right now, we're saying there are certain characteristics that influence the rate of the chemical reaction. Once we know those characteristics, then we can use them to our advantage, okay? The rate of the reaction is a measure of how fast the reaction makes products or uses reactants. So we'll start this chapter by looking at both making products. The chemical reaction we have, how fast is that making product? Or how fast is it using reactant? We'll use both products being made and reactants being used to measure the rate of the reaction. Towards the end of this chapter, we will focus on the reactants only because it makes it a lot easier to focus on just one thing. But we are being told in the beginning, you can focus on either the reactant being used or the products being made, okay? The ability to control the speed of the chemical reaction is very important. Okay, ultimately, sometimes we want the chemical reaction to occur faster. If that's our goal, we want to know how to influence the speed of the reaction without damaging or stopping the reaction. So besides studying about the speed, we're going to be looking at the reaction mechanism. So I'm going to go ahead and go straight to the factors affecting the rate of the reaction. We're told, number one, generally, that means let's say 90 to 95% of the time, the greater the concentration of the reactant molecules, the faster the reaction. Later on, we'll talk about the collision theory. Collision theory is a theory that talks about chemical reactions from a fundamental point of view. Okay? So, when we're looking at this, we're told here, in general, if the concentration increases, the reaction goes faster. Okay? So if you're looking at the concentration, for the most part, the higher the concentration, the higher the reaction. Concentration is a term that's used to describe solutions. And then pressure is a term that's used to describe gases. Okay, give me just a moment right here. Hold on. I'm responding to an email real quick. Give me just a moment. Okay, that I had to respond to that immediately, so I do apologize for that. Okay, so we do have increasing temperature increases the reaction rate for most reactions. So in this case here, if you increase the temperature, the molecules move around faster, they can find each other, and then the reaction rate goes faster. So once again, we'll talk about all these factors down the road, and then we'll try to relate that to the collision theory. Okay, if you increase the surface area, it causes an increase in the rate of the reaction. The surface area being increased causes a greater exposure, right? So here we're talking about the exposure of the molecules. When the molecules are more exposed, they can actually find each other, not really see, they don't have eyes, but they can find each other, collide with each other, and therefore react. For the molecules to react, they have to be in contact with each other. They have to find each other, they have to come close, and then they have to react. So when we're comparing gases, liquids, and solids, with the gases, what we see is gases move faster. So when the gases move faster, once again, they find each other quicker, and that makes the reaction go fast. Versus solid molecules, they're sedentary. So stuff will have to happen before these molecules actually find each other and therefore react with each other. The reaction will happen with solids. It will just take longer because we'll be waiting for the molecules to find each other. Okay? Catalysts, they're able to speed up the chemical reaction by altering the mechanism. So we'll study about catalysts towards the end after we have talked about the different mechanisms available. Okay? So now we're talking about defining rate. Exactly how do we define rate? Well, we're told here rate is how much a quantity. Now the quantity here will be either amounts of chemical, right? Amount of reactant or product. So at this point, you're trying to find how much the amount of reactant or product is changing over a given period of time. So in general, we're told here, the rate of a chemical reaction is measured in terms of how much the concentration of a reactant decreases or the product concentration increases in a given period of time. So I'm starting with the definition, this first one here. Let me highlight it. They changed these icons. I'm trying to get used to them. In the first one, we're told the chemical reaction rate, or the rate of the chemical reaction, is measured in terms of how much the concentration of the reactant decreases. So I'm spending some time down here using this equation to see how I have accounted for the information specified in that definition. Okay, we're trying to find rate of the reaction, right? So that's this right here in terms of the reactant concentration. I have the term reactant here to refer to. This is just communicates to you. I am monitoring the reactant only, right? In this equation, I can solve for the rate of the reaction. And in this case, I'm monitoring what chemical? The reactant only. It says so right here. What amount of the reactant, the reactant is measured in concentration, right? How do I know that? From the bracket. Bracket symbolizes concentration. That's the symbol that's used to communicate concentration. So when I'm looking at the reactant amounts, I'm looking at the reactant concentration. Okay, so what is happening to this reactant concentration? Well, it is changing according to the definition, right? Well, how is it changing? It's decreasing. So in this one equation, a lot of stuff is being communicated, right? It is decreasing. And it's decreasing according to what? A change in time. So this equation communicates the definition of the rate of the reaction when you're tracking the reactant. Okay? Remember, we figure out the rate by monitoring the change in concentration of the reactant with time. Okay? So this is where I stopped before, because right when I got here, my phone rang, and I have an iPhone and I'm working on my iPad. So then my iPad rang and it became a huge distraction. Anyway, I can figure out the rate of the reaction by looking at the reactant. But if I don't want to look at the reactant, I can figure out the same value, the rate of reaction, by looking at my product. If my focus is my product, once again, I have to look at the change in what? The concentration of the chemical type, which is a product, over change in time. So as time changes, how does the concentration of my product respond to that changing in time? Okay, let's try to make sure that this matches the definition they said right here. I'll use a different color, green. Or the product concentration increases, this time it's increasing, in the given period of time. So I have to make sure it's increasing. Now you can put a positive here to imply it increases. Or what chemists do, the positive is implied, so they leave it out. Okay, but the negative is never implied, so it has to be written, right? So here we're being told for the same value rate of the reaction, you can figure this out by monitoring the change in the concentration of the product as time changes. Okay, so this is the generic formula. You want to make sure you know the general formula because it comes up later on. If your minor is chemistry and you plan on taking upper level chemistry, junior level chemistry, you will see all of this 1412 again in a class called chemistry. That's all I would say. Physical chemistry. It has some calculus in there, it has some physics in there, and it has some chemistry in there. That's all I'll say for right now. Like I mentioned earlier, guys, we are going to be tracking our reaction. Now, we don't get to make a judgment here. The judgment got made for us. So we're going to confirm the judgment. Do we agree or do we not agree with it? Obviously, we agree with it because it's a textbook, right? The author wrote it, but let's see why this is true. Why is this labeled a reaction with a fast rate? I would recommend to you guys, if you see a question like this, the response from you should be to track. You're tracking, right? Track the changes from one box to another. You're trying to see what kind of changes are happening. So when you see this, your first response is count. Count particles to determine transformation. So what I'm going to try to do right here, y'all, is count. So I'm going to try to talk about what I'm counting so I can be counting the same thing, right? Okay, I'm going to start by counting A. And then I'll do B and C at the same time so I don't get confused. I'm counting A. Okay, A is this circle here. Well, it's not really a circle, sorry. A is like, it's like a capsule and it's bluish. It looks blue from where I'm sitting. And then B is a circle and it looks red. And then C is oblong and it looks green. Okay, so I'm going to go through and count A, B, C for every given time. This is considered the beginning of the reaction before anything reacted. So the reaction has not taken place yet, right? In the lab, we tend to start the timer when we are ready for the reaction to take place, not before. So right before the chemical reaction takes place, our time is equal to 0 seconds. How many A's do we have? By the way, at 0 seconds, we tend to have the maximum amount of the reactants. So go 1, 2, 3, 4, 5, 6, 7, 8. We got 8 amounts of A. How many amounts of B do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 amounts of B. Okay. How many amounts of C do we have? How many products do we have in the beginning? None, because the reactants have not reacted yet to make a product. So we have 0. No products, no babies, no kids, right? Then with time, the reactants react. How much time has passed? By the way, since these increments are huge, I'm going to estimate the time based on what I think it is, right? So I think it's around 20-ish. We're going to be happy with that. We're okay with that, right? 20-ish, 20 seconds. Okay. At 20 seconds have passed. Remember, reactants, I'm going to write on the side here, reactants decrease with time because they're being consumed, right? And then what happened to products? The opposite, they're being made. Products increase with time. So the idea here as we're examining this is we're approaching this from the scientific point of view, which is you approach things with hypotheses, prejudgments. But you remember that your hypotheses are subject to change if your data tells you otherwise, right? So we are approaching this knowing, okay, reactants are supposed to decrease as time goes by. Products are supposed to increase as time goes by. Let's see what's happening, right? So 20 seconds have passed. Okay, our reactants, starting with the blue ones, right? 1, 2, 3, 4. Oh, look, we only have 4 left. Now I'm only counting what is left, not what has reacted, right? There's only 4 left. And then the red, 1, 2, 3, 4, there's only 4 left. So if 4 of A, I can say here 4 reactants reacted, right? 4 of both reactants reacted. It just so happens that the amount that reacted is equal to the amount that is left. But when they're asking you questions, you want to know exactly what they're asking you versus assume. The amount you're seeing is the amount left over, right? So it's 4 left, and then this is 4 left. And then this one here, 4 got made, right? So you can see right here. 1, 2, 3, 4, 4 got made. So 4 of both reactants, and then 4 got made. Okay, let me remove these words from here because I feel like they're kind of crowding the space. Okay, so we're talk about stoichiometry because it's simple. We have a 1-to-1 stoichiometry. What that means for every, since the coefficient in our balanced equation is 1 to 1 to 1, okay? This means for every one amount, I'm leaving the amount as general because the unit wasn't applied, right? For every one amount, it can be 1 gram, 1 mole, or 1 mole, one amount of that reacts, one amount of B also reacts. Okay, this part is important. So sometimes it's easier for us to skim through the material until they ask you a question. And you're like, wait a minute, I didn't cover that. So you want to make sure you go through the stoichiometry because that matters, right? The stoichiometry here is communicating for every one amount, whatever that is, of A that reacts, one amount of B also reacts to produce one amount of C. I left the unit part general because they didn't specify it. I'm not about to specify it myself. Okay. Now the amount can be molar amount, it can be moles, it can be grams, it can be whatever. Okay. Now the time that has passed 35 seconds, right? How many do we have left? The blues, 2 left. The reds, 2 left. Ooh, now I can't spell left. 2 left? Y'all excuse me, okay? I'm recording in the evening. And then here, how many do we have now? 1, 2, 3, 4, 5, 6. A total of 6 made. 6 aren't newly made. 2 additional ones got made, but now we have a total of 6 made, right? And then here at what, 50 seconds? Oh, 0 reactants. The reactants are gone. 0 reactants. And then 8 made. So here are reactants. You started off with stoichiometric amounts, so there's no excess reactant. Both ran out. Here we can say it's finally the end of reaction. And if you were asked this, you say reaction took 50 seconds to reach completion, right? And based on the reaction, of course, you can say if you want this from here to here, of course, 4 amounts of each reactant reacted, right? It wasn't always the same amount each time. From here to here, it was only 2 amounts reacted of each reactant. I'm trying to write lists, right? From here to get to 0, again, it was 2 amounts that reacted. And each time that the amount that reacted equal the amount that got made, right? Because it's a 1-to-1 to 1 mole ratio. Amount reacted. Okay. So this reaction is sort of fast. It got done. It's over in 50 seconds. When the reaction is over, we have 0 reactants. Let's see what's happening here. Now we got X, Y, Z. And the timing, oh, it's the same time. We got 0 seconds, 20 seconds, 35 seconds, 50 seconds, all estimated, right? So we start with the green. 1, 2, 3, 4, 5, 6, 7, 8. Once again, we have a 1-to-1 to 1 mole ratio scenario. So for every one reactant, every one of the other reactant reacts to form the product, right? So let's say, did I count 8? I thought I counted 8. 8 here, right, of the green. 1, 2, 3, 4, 5, 6, 7, 8. 8 of the blue, and then the product pink, 0. Nothing is made because the reactions haven't even gotten together, right? Now they get together, they have 20 seconds together to react. How much product do they make? Look at that. Just one. I mean, seriously, guys, you had 20 seconds. These other guys here had 20 seconds and they made 4 products. You can already see, right? If you're tracking or following the product alone, the first reaction is faster because in 20 seconds they made 4 products. Here they only made one. It's going to be a long ride, right? To make one product, each one had to react. So we have 1, 2, 3, 4, 5, 6, 7, 7 left. 1, 2, 3, 4, 5, 6, 7, 7 left. It makes sense. Each one of each X and one of each Y had to react to make one of Z, right? It's the 1 to 1 to 1 more ratio. Okay, here at 35 seconds, how many more Z's do we have? Well, there's 1, 2, so we have 2 total Z's. That means one more got made. You're like, geez, how slow is this? That's why it's a slower reaction, right? 1, 2, 3, 4, 5, 6. We got 6 left here. 1, 2, 3, 4, 5, 6. We got 6 left here. Once again, one of each reacts. The reactant to form the product, right? So now we have this amount left over, and this is the product. Same time, now we have 50 seconds. Are we at the end of the reaction? No, because we still have reactants left over. We have 1, 2, 3, 4, 5. We have 5 reactants. So the first one, 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 of the second reactant. 1, 2, 3. 3 of the product. It's going to be a while before this reaction is over, right? So this is obviously a slow reaction. And this reaction has not ended. Why? Because we still have reactants. You have to keep going until your reactants zero out. Okay, now we're looking at defining reaction rates. So the first one here, I would argue this is defining the reaction rate by looking at a picture. So you want to make sure you know that. How to define rate from a model. How about that? The picture. This is a model. So make sure you know how to do this. I'm just telling you the type of questions, okay? When I was a student, I was thinking like a student, like stuff was happening to me and I had no control and I had to persevere and survive. At some point, I was like, no, I'm going to take back the power. Okay, I wasn't thinking like that, but I was like, you know what? I can anticipate what's coming. I went from feeling like stuff is happening to me in chemistry to thinking, wait a minute, I recognize this challenge. I've seen it before. And I said to see a pattern, right? So it got to a point where I said, seeing, oh, as we're working on this problem, I anticipate this kind of question being asked. I had a student that was so good at doing that. She would sit in class. That's when I was teaching organic chemistry years ago. Don't get any ideas. She will have her arms folded. And as soon as I taught something, she would look at me and almost in an accusation tone tell me, this is a good question for the exam. And I look at her like, I had just paused to think in my head, this is a good question for the exam. She looked at me and she said, it's going to be an exam, isn't it? I was like, get out of my head. Anyway, the point was, while it took me a while to figure, well, it took me like up until first year of chemistry to figure out, right? So I guess we were kind of the same level as far as figuring out what kind of questions you see. So she was thinking, this is the kind of questions I expect to see in the exam. She was thinking like a teacher, right? She used to do so well in the exams because she could anticipate what was a good kind of question, right? So, yeah. When you see the questions as they're giving you examples, think about it. Is this a good kind of question based on the learning outcomes? If you can think that way, not just in chemistry, in any class, they kind of tell you what the questions are going to be from the learning outcomes and the goals. So when they tell you that, you can kind of anticipate, right, what those questions are going to be. Just think about it. Okay, so now we're talking about defining rate. We're defining rate now and going further into stoichiometry. Now we have a balanced equation. We're told here the rate of a chemical reaction is measured in terms of how much the concentration of a reactant decreases or the product concentration increases. Didn't we say this before? Yeah, we're saying it again. But now we're actually going to do something with it. for reactants, a negative sign is placed in front of the definition, like I did before, right? Only they're doing it. We now have a balanced equation. So let's see right here. In our balanced equation, we have two reactants, okay? There is this one, and then there is this one. Okay, so what I'm going to do, I'm going to erase this one here because once again, it helps when you get what they're trying to say to recognize when they have switched the focus. Okay, right here they're telling you for reactants a negative sign is placed in front of the definition. So here the definition is the same thing as the equation, right? They give you a rate equation. We had the balance equation. In the balance equation, while we had two reactants to pick from, they only decided to focus on I. So they're writing this rate equation, but from the point of view of I. I is the focus and I is the reactant. We know that reactants decrease in concentration with time. So reactant, I'm writing it again, concentration decreases with time. So for that reason, you have to have a negative sign. So I'm going to tell you right now, all rates in chemistry are positive. So let me write a little caveat here. All rates in chem are positive. Okay? So when you know that, it helps you. So just say you forgot, right? You're doing some kind of MCAT or something and you forgot. If you remember this and you get a negative rate, you're like, wait, why is my rate negative? Maybe all the answer choices are positive. You're trying to reconcile that logic. All rates in chemistry are positive. The chemicals are always reaction. They never, sorry, the chemicals are always reaction. They never de-react, right? So as you're making the product, if the rate is fast, then you have a large rate. So large rate equal fast reaction. Okay. Small rate equal slow reaction. Okay. So because the concentration of the reactant is decreasing, okay, I want to say right here, the reactant, let me call it R because writing the word reactant is just taking up a lot of space. We're going to do the reactant final concentration minus reactant initial concentration to figure out the difference. Once we subtract those two, since the concentration amount is decreasing, the final number will be smaller than the initial number. Just in case you want to know, this would be a larger number. So when you take a small number minus a large number, you get a negative number. So negative times negative gives you positive. Okay? The difference, the change in concentration of the reactant concentration, think about that, is going to be negative. Negative times negative is positive. So we'll work this out so you can see. Okay, so where was I? We're right here, yep. And they picked this one here. And then when it comes to illustrating this, just like I did right now, they choose a different symbol. This kind of thing upsets me, okay? I'm like, we were talking about I, though. How did you change to H? See, I'm not the only one who switches stuff, right? Sometimes my brain just switches stuff. It's like I'm bored with this letter. Can we go to a different one? They do that here too. I can't change this because it's a picture and I don't know how to get it to this exact format. So I leave it as is, but I talk about it. The rate of the chemical reaction over two time periods can be written as follows. So here they change the focus and now we're looking at H2, the other reactant, not I2. But the idea is the same. It applies to both. The rate of the reaction is still a reaction, so it's negative. Change in the concentration of H2 over delta T. Now remember, 2 here, this is essentially final condition. 1 for the time is initial. Okay, this T2. So T2 is when the time that the time of the reaction is over, when the reaction has ended, or whatever you decide is the stopping point. That stopping point versus the starting point. So T1 is starting or the start of the reaction, and then T2 is the end of the reaction. So the end minus the beginning gives you that difference, right? Okay. So before we continued here, I wanted to introduce something before I forgot. Now, I realized that maybe I may have been a little premature because I wrote this earlier before I started teaching the actual lesson because I told you I had so many false starts today. Wait, how are these different? Okay, so let me go ahead and actually move this over. Wait, let me move this over. Wait, what happened? Oh no. Okay, hold on. I was here. I just wanted to have this move down. Okay. Let me add a page down here. That's okay. I'll add this right here and I'll deal with it when I get to it here. I'm trying to deal with this new, yeah, I'm not going to re-record this. I'm just going to go with this, whatever. Okay, I'll write it myself. I can rewrite it because since I wrote the first one. I'm really struggling with all, they updated my app. It's not really, my app, but they updated the app. And so I'm struggling with the new changes 'cause I'm not very familiar with them. Anyways, let's look at the rate of the reaction and the stoichiometry and how it plays out. So we're being told here for these reactions, when you have a reaction where stoichiometry is a factor, the change in the number of molecules of one substance is a multiple of the change in the number of molecules of another substance. So here we're being told stoichiometry does matter to prevent the rate from being different. Wait, what? The rate can be different? Remember I told you earlier, you can get to the same rate by tracking any reactant or any product. But if you don't take care of stoichiometry, you can have different rates. So it's saying here, to prevent that from happening, the change in the concentration of each substance is multiplied by, there should be the word multiplied, is multiplied. I feel like there's a formatting issue here, by 1 over the coefficient. Okay, so what they're trying to say here, let me go ahead and add a page. This should be simple, just add a page. And I'm going to move this over. Hopefully that will work out well since they have a new feature here. Copy this over. Now show you what they mean by this. Okay, remember, the goal here is to communicate. This is the goal. Rate can be calculated by tracking any chemical in the balanced equation. That's what they're trying to communicate here. Okay? So they did so by saying rate equal this and this and this and this. So let's go ahead and figure out our own rates. We'll figure out, since we have 4 chemicals, we'll figure out our rates. Okay? It's the same value of rate. Okay? Rate equal. According to them, they say that multiply each of the change in A over change in T by 1 over the coefficient. So I will do that. Rate, I'll start with the reactants. So I'll say here reactants. For my reactants in the balanced equation, my rate is, remember reactants, I'm going to write here to remind myself, decrease, therefore negative. The rate here will be rate equal negative, right? Because of the decrease part. You put in negative for decrease. And then you have a change in the concentration of the reactant. So I'm going to start with reactant A. Change in A over change in time. Okay? I can get the rate this way, or I can get the rate using the other one. Negative. I'll come back to the coefficient. I'm not done. Change in B over change in time. But if these coefficients are numbers that are not 1, then I have to multiply them here. Okay, so I have to multiply them here. Take this number times 1 over A, the coefficient of this. Here times 1 over B, the coefficient of this. So this becomes equal to negative 1 over A delta A over delta T. This becomes negative 1 over B delta B over delta T. Okay? So that's how I'm going to be dealing with the reactants. Now I'm going to be dealing with the product. I'm going to give a general term here where I bring in what I raised earlier. Okay? So over here, for my products, though, I got C and I got D. Okay. Since I'm dealing with products are increasing. Increase. So remember, we're going to use a positive or leave it out. We're going to say here, rate equal change in concentration of the product. The first one was what? C? C over change in what? T. Second product, rate equal change in concentration of D over change in T. Now go back and look at your coefficients. C had a little c in front of it, so I got to multiply 1 over, right? That's what they said, times 1 over C, which is going to be 1 over C delta change in big C over delta T, okay? Times 1 over D, 1 over D delta change in D over delta T, okay? So these are my products. So they're going to be positive. You can put a positive here if you want to. If it really bothers you, you can do that, okay? Okay, so here's the thing. You want to be familiar with problems and how scientists describe problems. The thing with chemistry, it's more in chemistry than it is in biology, if I recall biology correctly. With chemistry, sometimes they're asking you something you already know, but they're using different terminology. If you're not familiar with terminology because you didn't spend time to remember or memorize that, you have no idea what they're asking you. And I hear that a lot. Well, I have no idea what they're asking me. And I usually ask this question. When you were reading what they were saying before in the questions, were you rushing to answer it, or were you paying attention to how you were being asked? Right? You kind of have to learn how they're asking you things so you can know how to answer them. So one of the ways they're going to ask you this question here is, I have seen this, so I made note of that. They can say in general, rate for the reactant equal negative 1 over the coefficient, right? Like we just saw, right? Times, you know how you have change of B over change of A? That's sometimes called the rate of disappearance. Okay, so I have seen questions where they're asking you, calculate the rate of disappearance. And I'm like, what? These words were never used, but they want you to understand reactants disappear as they decrease with time in the chemical reactions, while products appear. So you want to be aware of this alternate way of writing the rate of the reaction. 1 over coefficient times rate of appearance. Okay, you want to be prepped. So now you know if they ask you for this in this context here, your rate of appearance will be, of course, delta C over delta T, or delta D over delta T. Yeah, if they're asking you, they're really asking you for one of these. Appearance of the product. Over here, do I have room? This means delta, was it A, right? Over delta T, or delta B over delta T. So we'll work out a problem so you can see how it plays out. Remember, you guys are watching a recording, so feel free to rewind until it makes sense. Work out problems, that way you get the hang of when they're asking you stuff and how they're asking you. If they want just the regular rate of the overall reaction, they tend to say rate of the reaction. When they say stuff is appearing, stuff is disappearing, they want you to find the rate as it pertains or depends on the reactant. Only they have to tell you which if there's more than one reactant. Okay? So let's get to this question right here. Okay. Let me get some water. Okay. So it says here, consider this balanced chemical equation. So here we have a balanced chemical equation. Let me copy this. My stoichiometry right here. Oh, I got some room already? Okay. I got some room. Ready to go. Okay, here's my balanced equation. What are they saying? In the first 10 seconds of the reaction, the concentration of I minus drops from 1.000 molar to 0.868 molar. Okay, that means if it's the first 10 seconds, that means the initial time was 0.0 seconds, okay? And then the final time is 10.0 seconds, right? When time was 0.0 second, before anything happened, the concentration of I, so we're told I minus, right? Its concentration was this number right here. So I'm going to write this as 1.30, like that, right? And then it dropped to 0.868. I minus dropped to 0.868 molar. Now you can write this as IT1, IT2. I just write it as like 1 and 2, or initial and final. I don't want to complicate this, so I just say initial, final. Then maybe I can make this, like, I can be consistent here. How about that? Initial, final. Okay. Yep. What do they want us to do again? Calculate the average rate of this reaction in this time interval. So we want to figure out the average rate of this reaction in this time interval. Then what are they asking us next? Determine the rate of change in the concentration of H plus. Oh, they want us to figure out the rate of change, focusing only on H plus. So the question they're asking us here, the rate of change of H plus is the same thing as rate of disappearance of H plus. Okay, they could ask you this way like they asked, or they could ask you this way and you'll be solving for the same thing. Okay, so I'll redefine this when we're covering that part. Let me do the first one first. So remember rate, we're dealing with a reactant here. Oh, come on. I'm not stopping this time. Rate, we're dealing with I minus. I minus is a reactant. So let me pretend to forget the negative sign. I'll pretend to forget it. Okay. Change in I over change in T. I'm really trying to focus here. Okay, we're trying to figure out the rate of the reaction. They only gave us I minus, right? Remember the stoichiometry factors in here because you have different coefficients, so you have to include the 1 over 3, right? Times change in I over change in T. So this will be 1/3 change in I. Change in I will be the final minus the initial, so 0.868 minus 1.000. Remember, this is M over the final time, 10.0 seconds minus 0.0. This is seconds, right? I mean, you can put the M both sides if you want to. I just left this out here. Let me be consistent. It's the small things. Okay, there. So I'm going to forget the negative on purpose so you can realize that, remember, rate is always positive, so you're going to need the negative there. Just in case you forgot it, just bring it back in. 0.868 minus 1. Oops. I haven't brought in the negative yet. I'm resisting the urge to do so. Negative 0.132 divided by 10, right? So we got m over s. So we got that number divided by 3 divided by 10. And I get this number right here. Okay, now if I forget the negative, I end up with negative 0.0044 meters per second. But remember, the overall rate of the reaction is always positive, so this has to be positive. So of course, to do it correctly, I should have had the negative here to begin with, and that's what will fix this and make this positive. So the rate of the reaction is this. That's the average rate. Okay, so just in case you forget it, remember the overall reaction rate is positive. It's only when you're dealing with a reactant only and they're trying to figure out how is that reactant changing with time. Only then do we have a negative and a positive value. Negative implying that concentration you're focusing on is decreasing with time. Okay, so here with this question here, the second one, determine the rate of change in the concentration of H plus. So we are trying to find H plus alone, not the whole reaction. Here it was the whole reaction. Here is H plus alone. So H plus is a reactant, so we know it's going to decrease with time, right? They tell you that is delta H over delta T during this time interval. Here's the thing. I told you before, you can figure out the rate with any of those reactants, right? So we know from our balanced equation, what is the coefficient on H? It's going to be 2, okay? The same rate we just figured out is equal to negative, since H plus is a reactant, 1 over 2 times delta H, right, concentration, over change in time, okay? What do they want us to figure out? Delta H in concentration over change in time. Remember, delta H concentration over change in time is the same thing as rate of disappearance. I feel like I didn't spell this properly, y'all. Let's go back and do this right. Disappearance, yes, of H plus, or rate of change according to H plus. Okay, two different ways of saying it. They want you to solve for this. So trying to solve for this, remember we just solved for rate. Rate is up here. So we have this number. This rate is 0.00. Do I have it in my calculator? Yep. 44 meters. I'm not meters, sorry. This is molar per second. What was I thinking? Meters. Hold on. Let me rewrite. Oh no. Come on. I'm trying to get the positive version of my answer since I'm trying to make a point, and now I have the wrong version of my answer right there. Okay. 0.0044 molar per second equal negative 1/2 times the variable we're trying to solve for, right? Delta H over delta T, and this is the concentration of H. We're trying to solve for this. So go ahead and you can divide this by negative 1/2, divide this by negative 1/2, and let's see what we get. So take your number, 1 divide mine by negative, open parentheses, 1 over 2, close parentheses, and I get this as negative 0.0088 molar per second. This is the rate at which delta, the H plus concentration, oh, I forgot the plus is right here, is changing with time. So in the same 10 seconds, this is the amount of H plus that reacted, okay? It decreased by that amount. So this is kind of how you can tell each of those reactants. Imagine you giving a shape, right? This is a, say, a square, and this is a triangle, and this is a circle. You can show after 10 seconds, the circle amount should be less by this amount right here. Okay, and they told you the amount. Yeah, you should be able to figure out the amount by which I minus will also be less, which we didn't really work it out that way, but you can just do the change in this, right, over time here. Subtract these two, divide by 10. So it should be, looking at this right here, it should be like 0.0132. So the amounts don't matter. I mean, sorry, they shouldn't say they don't matter. They don't match. Sorry, they don't match, right? The rate at which I minus reacts doesn't match with the rate at which H plus reacts because they have different coefficients, right? Probably have different starting amounts. Okay, anyway, hopefully you've seen that. They work it out, they get this, they have scientific notation, everything is written that way. They work it out, they get this one too. So you want to be aware of how to figure out these problems and solve them. Okay, they do have this one here. Oh, you can predict the rate of change of the following right here. You can go ahead and do that. If you have questions about this and you want me to work more of it, let me know. I'm trying to work on a deadline here. So I'm going to end with this, finding the rate law using the initial rate method. Since I found out while I was doing my 7th take that we're not going to be having class tomorrow, then what I'm going to do is continue to record this privately and then post it. And whenever you can watch it, you can watch it, okay? So there's something called a rate law. So before we try to find it, what is the rate law? What we've seen so far is figuring out the rate from either tracing or tracking the product or the reactant. There's something called the rate law. And I call the rate law, I say the rate law is similar to the point slope form equation of the line. You know the point slope form equation of the line where you have y is equal to mx plus b. It's not equal in purpose, but it's equal in the style. When you look on the format, I would say, when you look at the way this equation is written, some parts of the equations are variables, some parts of the equations are constant. So when you look at the equation of the line, the point slope form, the y and the x are variables, so they're left as a variable symbol. You leave the y and the x as a symbol. Then m and b, because they're constant, you write those in there. In the rate law is technically an equation. And it's an equation that communicates something. The rate law communicates the effect of each reactant on the rate of reaction. I try to simplify my definition and I only complicate it when, well, I shouldn't say I wish. I complicate it when I have to add more information, right? So let's start with simple. We're going to always add to it. The rate law is an equation. So I'll say here, an equation, and it has a purpose, right? What does it do? It communicates the effect of each reactant on the rate of the reaction. So going back to what we just experienced, apparently the reactants can change in different amounts in the same given time if the coefficient is different. So you can say that each reactant can influence the rate differently. That's a possibility, right? The rate law is not a law that says, well, when this happens, that happens. It's not that kind of law. It's an equation that communicates the behavior of each reactant and its effect on the overall rate of the reaction. Okay. So, oh, by the way, I forgot to mention this. From here on, we are now focusing on reactants only. This shift has happened. We are focusing on reactants only from here on, okay? So as we're looking at this, hold on a second. I feel like there's a page that got missing because I was trying to show you guys something and there's a page with the graph. As I was scrolling through, this graph right here. I need to communicate something important, so I don't know how it just got missing. With this new page, this new app or the updated version, some parts of it is super sensitive, some other parts of it is just, yeah. So before I move over to this, I need to talk about, hold on, paste. Okay, let me delete this page here. Okay, so we're right here. Okay, before we start focusing on the single reactant, we want to look at the graph. You want to be able to interpret. So we're talking about interpreting the graph. Okay, one of those learning objectives written in the syllabus that you need to know how to read the graph. Okay, we want to know how to interpret the reactant and the product concentration changes as a function of time. How is the reactant concentration changing with time? How is the product concentration changing with time? So as we look at this table here, this graph, our focus is to answer those two questions. How does reactant concentration change with time? And we're doing the same thing for the product. How does product concentration change with time? Okay. So as I look at this here, this is the last time we're focusing on both. From here on, remember, we're focusing on reactants only. This picture, by the way, this graph here, is illustrating what is going on in this balanced equation that we saw earlier. Now, they chose to focus on one reactant only, right? Because I recognize, even though we have two reactants, H2 and I2, they chose H2 for whatever reason. That's what's being featured here. They could choose both, and they'll use a different color for I2. They chose H2 only. And then for our product, we only have one product. It's right here. So here's the bottom line. They're communicating that at time 0, the x-axis is time in seconds. We go from 0 to 120 seconds. Yeah, in seconds, right? And then concentration, we go from 0 to 1.8 molar concentration. That's your y-axis. Okay, so I'm going to trace or track the amount of my reactant H2. In the beginning of time of the reaction, before anything takes place, we have the maximum amount of the reactant possible. I would say maybe around 1 molar, right? Around 1 molar. And then the reaction takes place. As time goes by, the reaction concentration, the concentration of the reactant concentration decreases, right? A little bit reacts, it starts reacting. So we're only tracking the amount that's left over, not the amount that's reacting. The one left over decreases until the reaction ends where this drops to 0, right? Meanwhile, in the beginning of the reaction, there's no product. It begins to get made and made and made, and then a lot of it gets made, and it keeps getting made until either one reactant runs out, the limiting reagent, or both run out, and the reaction ends. Eventually, this will flatten out because you make the maximum product possible. Eventually, this will deaden out because you run out, and it'll be over. The reaction will just end. Okay, so this picture shows you both the product behavior right here and then the reactant behavior right here. I remember years, just so many years ago, when we were asked to sketch these things. So you have to understand it to be able to sketch it, right? Reactant concentration decreases with time until it ends. Product concentration increases with time until it ends. So you want to be aware of that. Okay, back to what I was talking about right here. Now that we're talking about the purpose of the rate law, remember, it says right here, before we get into it, we have like a warning sign, warning. Rate law must, this is a must here, must be determined experimentally. Now, we will use calculations, but there will be a data table provided. Data table from experiment provided. Okay, so don't check out and say, well, I don't have time to do experiments, so I can't do this. No, all they mean is you have to use a data table that came from an experiment, and then from there you can figure out the rate law. That's an equation, right? The rate law shows how the rate of a reaction will change if we change the concentration of either reactant, assuming there's more than one reactant, right? How each reactant's concentration change influences the rate of the reaction. Changing the initial concentration of a reactant will therefore affect the initial rate of the reaction. Okay, so let's go ahead and see an example of how this plays out. The rate law, the effect of concentration on reaction rate. The rate law of a reaction is a mathematical relationship between the rate of the reaction and the concentrations of the reactants and homogeneous catalysts as well. So bottom line, this is a generic form of the rate law. So when they ask you for rate law, the answer you're looking for is something that looks like that, but that's the generic form. So you tend to adapt it to the question they gave you, right? So I'm going to tell you this. The term rate remains as the word rate. So, right, rate. Leave it as rate. And then when you're asked to provide the rate law, leave as K. There's only two parts here that get replaced. A replace with, I need space, formula, right? The chemical formula. And then N is replaced with a number. So rate and K are left as is. N replaced with number. Like I was saying earlier, it's kind of like the point slope form of a line, the equation of the line, where some parts of variables are left as is. So the rate in this case here is left as the word rate, and then K is left as the word, as a symbol K. Okay. So what I mean by that is, in general, we're being told based on this equation right here, the rate of the reaction is directly proportional to the concentration of each reactant raised to a power. Sometimes they use this definition here to define the rate law, what it is. So the other definition we looked at before was more about what it does, or what it is important for. This one here is more like what it is, or what it symbolizes, what it shows, right? It shows here the rate of the reaction is directly proportional to the concentration of each reactant raised to a power. So let's go ahead and apply it. We have a balanced equation here, A with a coefficient of A plus B, coefficient of B, to form products. So one of the things chemists do is they focus and they kind of, I don't want to say fixate, but let's look at it like fixation. They fixate on reactants in this section right here. Since we are fixating on the reactant and ignoring the product, even though they are formed, we just leave product as the word product to communicate that we are only focusing on the reactant. Okay? So you're told, when you're given an example like this where A and B are reacting to form a product, if you were asked to write the rate law, you will write it like this. The rate law, okay, will be written like this. Rate, the word rate, equal K. The brackets represent concentration of A is a chemical, the reactant, raised to the power M. B, the other reactant, raised to the power N. They were sure to write the coefficients here as A and B, and the powers as M and N, just to let you know that M is not equal to A and N is not equal to B. So what are they trying to communicate? They're trying to say that these powers you're going to have in the rate law are not the coefficient from the balanced equation. Okay, so M did not come from the balanced equation. N did not come from the balanced equation. They came from somewhere else. Okay. Once again, guys, feel free to rewind. So let's go ahead and actually get to a real question where we have data from experiments. Here we're told determine the order and the rate constant of the reaction. So one thing I want to do is, because since I don't know, I feel like a lot of slides were skipped for some reason. I want to go ahead and define what the order of reaction is. M and N are actually called orders of reaction. Okay, so let me go ahead and add a page here and define that. Since M and N are not coefficients, M and N are not coefficients from the balance equation. No, they're not. But they are called order of reaction. M shows how reactant A affects the rate of reaction, and N shows how reactant B affects the rate of reaction. So they are not the coefficient of the balanced equation. They have a purpose, and that's to communicate how these reactants here influence the rate of the reaction. Okay. Once again, as you watch this video, if you have questions, write them down, shoot it to me in an email. We can't have traditional class because y'all probably got the message school is out till Monday. But I don't want you guys to fall behind because time will not be generated, right? So, yeah. Okay. So here it says, determine the order. In other words, since we have two chemicals here, M and N. Find M and N. I have to say, and the rate constant of the reaction. Okay. So as we're looking at this here, it says NO2 plus CO form NO plus CO2. So this consider the reaction between nitrogen dioxide and carbon monoxide. So we have these two. The initial rate of the reaction is measured at several concentrations of the reactants with the results shown in the table from the data table. Where's the table? Oh, all the way down here. I need that table. Oh, okay. What I'm going to do, since the table is all the way down here, let me copy the table. I need that to solve the problems. Okay, so let's pretend it's up here, like I just moved it right here, because I need that to do my work. Okay. So initial rate of the reaction is measured at several different concentrations of the reactants with the results shown in the table. From the data, determine the rate law for the reaction. Remember, rate law has the format rate equal K, open parentheses, reactant, raised to the power M. Repeat this for all the reactants you have. And then after we do all that, they say the rate constant. Oh, solve for this K. What is K equal to? Okay, I can do that. Okay, so here's my thing. I'm going to be figuring out the rate law. Let me not be lazy. Since I have two reactants, I'm going to have two reactants in my rate law, right? That's what I think. I'm hypothesizing. It will look like this. Rate equal K, and then I'll have my first reactant. So I'm writing a little slow, smaller, raised to the power M. Second reactant, I should call it reactant 2. Reactant 1 raised to the power M. Second reactant 2 raised to the power N. It will look more like this. Of course, I'll go in there and write what the reactants are. I will solve for M and N, and that will help me complete my rate law. After I'm done doing all that, I will solve for the rate constant like they're asking for, which is K, the symbol K in all of this. Okay? Well, how do we solve for M and N? Here's the thing. To solve for M. Let's start with M. I will write my rate law. Okay. I need my balanced equation though. Let me copy this over. I'm I'm so used to recognizing my symbols by how they look. Now I have to remind myself it looks different. It looks different. Wait, I already copied this, didn't I? Copy. Oh, come on. Okay. Yeah. So I'm trying to solve for M. So what you're going to do here, to solve for M, you're going to be using the rate law, right? You will write the rate law for each experiment. So here we have 4 experiments, 1, 2, 3, 4. You will pick 2 out of the 4 experiments that have a certain criteria, and then you write a rate law for them and then work things out. So to solve for M, I'm trying to solve for M. First of all, I need to write a mock rate law. My rate law will look something like this, okay? So this is my presumptuous rate law. My rate law will look like this. Rate equal K. My first reactant is NO2. NO2 raised to the power M. The other one will be CO raised to the power of N. So I know my rate law is going to look like this. I'm going to solve for M. I'm going to solve for N. And when I solve for those, that completes my rate law, right? So to solve for M, I'm starting with this part here first. To solve for M, I have to pick 2 experiments. Those 2 experiments, as I'm trying to solve for M, I want to keep CO constant. I want to keep CO from influencing the observations I'm having. So to solve for M, which goes with the formula NO2, right? Keep CO concentration constant. That's the goal here. So select 2 experiments in which the concentration of CO is not changing. This is our goal right here. Pick 2 experiments. So I'm going to write what I'm doing here. Pick 2 experiments in which concentration of CO doesn't change. Okay? CO, 0.1, 0.1 doesn't change. Will that work? Sure. So I'm going to pick experiment 1 and experiment 2. And for our purposes, I'm just going to give a shortcut. I like the big numbers on top. So I'm going to work here and say experiment 2 divided by experiment 1. Okay? So write your rate law. So in other words, I'm going to do rate 2 over rate 1 equal K NO2 M. Oh, let me actually work this out and plug in the numbers so it'd be a lot quicker because I feel like I'm just going on and on. So let me go ahead and work this out so it'll be a lot quicker. Okay, what's rate 2? This is the initial rate. This is the number I need right here. Rate 2, 0.0082 here. 0.0082. What are my units? Molar per second. Molar per second divided by equal K. So I wrote this rate part, right? And I wrote this K part, okay? And over here, I need to write the NO2 part. What is the NO2 for experiment 2? Because this is experiment 2, right? NO2 for experiment 2 is what? 0.2. 0.20 M. And then this is going to be raised to the power M. I have no idea what M is. And then for CO experiment 2, that's going to be 0.10 raised to the power N, right? All of these are information about experiment 2. Divide that by information about experiment 1, starting with my rate. So I have to start with rate for experiment 1. What is that? 0.021. Wait, is it 0.021 or 0.0021? You need to copy those correctly. Don't be like me. Do better than me. Go out there and do better. 0.0021 also molar per second. I don't know what K is, but K is part of that rate law. So essentially, I'm writing the rate law for experiment 2 over rate law for experiment 1, just in case you're wondering, okay? For experiment 1, my NO2 concentration is what? 0.10, 0.10 molar raised to the power m. This is the same thing, right? For CO, we kept CO constant, so it's going to be the same number, 0.10 raised to the power n. Okay, so we take rate law 2. I guess I should write this like rate law 2, right? Rate law 2 over rate law 1. That's what I did here. Units cancel out, K's cancel out, this cancels out. Look at how much it makes our math simple, right? Because chemists are like, listen, life is already tough enough. Why should we make our math any more difficult? So I got a 3.90. I divided these already. 5 equal 0.20. Oh, the m's in here cancel out. Power m over 0.10 power m. So there is a rule in math that says when you have numbers with the same exponents, you can consolidate them, right? So we're going to consolidate these two. They become 0.20 divided by 0.10. And then the exponent applies to the numbers, the base numbers, 3.905. Now this ends up being 2 power m, and then this number is close to 4. You can round up to 4. Now the way the book works it out, they use logarithms. You can do that, but that's junior level is where you need to do all that log stuff. I think at you guys level you can coast without doing the log. Essentially, you do the log of 4 divided by log of 2, all that stuff, and then you get your answer. You can do that if you want. They show it out in the book. I'll show you how they work it out. I like doing the exponent form is a lot quicker. Okay, this here, you want to write 4 as a number of base 2 where the value is the same. So 2 power 2 is equal to 4. You want to rewrite it, the number where the base is 2. And then 2 power m. So if the base numbers are the same, the exponents are equal to each other. The base numbers are equal, the exponents are equal, therefore m is equal to 2. Okay, we just solved for m. Now that we have m, we can do the same math, but this time we're doing it to solve for n. To solve for n, we have to keep NO2 constant. To solve for n, keep NO2 concentration constant. So our goal here in picking our experiments is with that in mind. You want to keep NO2 concentration constant. This is the logic behind it. If you're a logical thinker, you would appreciate the logic. When you're doing scientific experiment, you don't want to have too many variables, too many things changing. That way, if you change one thing, if you stick with changing just one thing, you can tell the change in the results is due to that one thing. If you have more than one thing changing at the same time, how do you know what was the one that gave the results? You don't know. You're going to just speculate away. So here we're changing. If we're keeping NO2 constant, we're only changing CO. So whatever change in the experiment we have is due to CO. Then we can tell how CO influences the rate of the reaction, right? So now I'm going back here. This is so far away now. Let me copy this over because I'm struggling with scrolling back and forth. My eyes from looking at the screen this whole time. Okay. So, hold on a second. Let me move this over here. Now, oh, I can't even erase because that's the picture now. Okay, sorry. Okay, so now I have to look for an experiment. Hold on a second. My eyes are really burning. We're going to be looking at an experiment this time in which NO2 is kept constant, right? You probably can figure that out. Hold on. Ooh, okay. After this, I'm done. I need to give my eyes a rest. I'll watch the TV screen instead. It's a little far away from my eyes. Okay, so experiment 2 and 3, right? NO2 is constant. So we're going to be doing 2 and 3. 2 and 3, which is bigger. The numbers in 2, this is bigger than that. So we're pretty much going to be doing experiment 3 over experiment 2. And let's see, we're going to do rate law for experiment 3 over rate law for experiment 2, right? So we start with the rate, which is 0.0083 molar per second over 0.0082 molar per second equal K over K, concentration of NO2, NO2 raised to the power. Since we already know what the order on NO2 is, what was it? 2, right? So you can write it here. Go ahead and write it in because it helps you with other problems. NO2. Oh, I'm supposed to write the actual numbers. Focus. It's towards the end, right? I'm already thinking about what I'm going to be doing. Let me focus on this. NO2 is supposed to be what? 0.20 raised to the power 2. Here it's still 0.20 raised to the power 2. Now we're looking at CO. CO is supposed to be 0.20 raised to the power n. We have no idea what the order is. This is 0.10 raised to the power n. Right? We're trying to solve for what is n. Okay. Now that we have all experiment 3 stuff on top, 2 on the bottom, we can work this out. This and this cancels out. The units cancel out. This cancels out with that. Even though we have it solved, it still cancels out. Now I'm going to divide these two numbers. It comes up to 1, y'all see. It's so close to 1, right? So now I'm left with 0.20 raised to the power n over 0.10 raised to the power n. I'm going to consolidate this and get 0.20 divided by 0.10 raised to the power n. What are we dealing with here? This is 2, right? Divide these 2 raised to the power n, and we got 1. Now we have to rewrite the number 1 raised to the power, we have to rewrite the number 1 having a base of 2. So go back to your math rules. Any number power 0 is equal to 1. So 2 power 0 is equal to 1, right? Because any number power 0 is 1. So we want the number to have a base of 2. So 2 power 0 equal 1. That replaces 1. 2 power n. So then if the bases are the same, so are the exponents, right? So n is equal to 0. Okay. Have we answered the question yet? No. All we did was figure out the orders of the reaction. So what does this mean, by the way? What do these orders mean? Let me write the rate law, and then I'll tell you what it means. Now that I have these, I can write my rate law. The rate law is equal to the following. I'll write it as rate equal. You remember, you leave the word rate as rate. K, open parentheses, NO2, open bracket, NO2, close bracket, raised to the power 2, and then CO raised to the power 0. Remember we said anything raised to the power 0 is 1. So the rate law is really rate equal K NO2 2. This is the answer. This is our rate law. Okay? Okay, what does this mean? You need to know the implications of this. This means that, when NO2 concentration doubles, the reaction rate quadruples. Because it's squared, right? So it quadruples. It doesn't also double, it quadruples. If it was first order, it will actually double. It quadruples. When CO concentration doubles the rate of reaction does not change. You're wondering, why doesn't it change? Because it's a zero order. Zero order just means the reaction rate does not change according to the reaction rate does not change in response to changing that chemical. So say, for example, to kind of make this more relative, if you were in a company and you were working on this reaction and your boss said, make the reaction go faster, your best bet is to change the concentration of NO2, because anything you do to that, you square it and you get the change in the rate law. If you double this, this quadruples. If you triple this, square that, you get the rate. That's how it influences the rate, right? The double and the quadrupling is a lot easier for me to say. Whatever number you put in here, whatever change you do to NO2, you have a significant change with the rate. But since CO doesn't even appear in the finalized rate law, if you try to double this, you're wasting chemicals. And you're wasting the company's money, okay? When you're working for a company, you're trying to get a bonus so you can get your ride or whatever it is you want, a vacation. I don't know what your goals are, right? I don't know. I know what my goals are. That vacation, that ride, that purse. Yeah. So this one here, if you try to change the concentration of that, you will not be influencing the rate, so you just be wasting chemicals. So you want to know that. Now, is this chemical important? Yeah, without it, the reaction won't take place. But is it important in making the reaction go fast? No, it's not, because it's a zero order chemical. Okay, so hopefully you understand that. Now that I've said all those words, what was the other part they wanted us to do? They wanted us to find K. And then we're done. Well, for tonight. Just for tonight, y'all. Just for tonight. Okay. So after all that, I know rate law is equal to K NO2 raised to the power 2. There's no CO in the final rate law. Now they said solve for K. That was the second part, right? You have 4 experiments to pick from to get your numbers. Pick any 4. I tend to like the easiest one, which is the first one. So I would say I will using experiment 1. You can use any of the experiments provided. I'm going to use experiment 1. For experiment 1, I'm going to use these numbers right here. So my rate is the number on the right, 0.0021. Don't forget the units. Units matter in chemistry. Molar per second equal to K. We're trying to solve for K. What's the concentration of NO2? NO2 is 0.10. 0.10 squared. Okay. Okay, where was I? I guess I could divide. Oh, I'm a hypocrite. I know I just said units matter and then I forgot it. Listen, I'm constantly judging myself anyway, so like there. Okay, because I'm like, where are the units? Divide by 0.10 molar squared, divide by 0.10 molar squared. Okay, so this cancels out, so we're left with K. So this is going to be 0.0021 molar per second. Let me square the bottom part. 0.1, where's my square? Square. The number squares and gives us 0.01, and then the unit becomes m squared, right? Don't forget, you're squaring the unit and the number. So one of the m's cancel out with the top m's. We're left with one m. So the number, as far as the number is concerned, we have 0.0021 divided by 0.01, and we end up with 0.21. 0.21 1 over molar second. This is K. You can look at it this way, or it can be written as 0.21 m power negative 1 s power negative 1, and this is going to be K. Mathematically, these units are alike. right? If you don't like fractional units, you can bring the denominator on top, but you raise it to the power -1. I don't know the math rules right now. Okay. So they go ahead and they work it out. They use a very different method. It's a more direct method on how to get the orders of reaction. You can see that. It shows you here. NO2 has a second, they call it second order. Second order. This one here is called zeroth order. So when you have a zero order reaction or zero order reactant, it's sometimes called zeroth order. I don't know why they named it that. That's what they named it, zero order. When we go through the whole reaction, they show you different ways. You have the exponent form, then you have the log form. The exponent form was the one that was up here. I used that one by approximating this into 4. They have the log form right here where they do all that, and then in the end they approximate. I'm like, why do all the logarithm stuff and then still approximate, right? And then they work this out. They do all this, and they get the final answer for the value of K. Okay. If you have any questions about this, please send me email before I do my recording for tomorrow so I can go ahead and actually address this. I'll try to do my recording whenever it's convenient based on what's going on right here. So it might happen in the around 11, maybe not. Just let me know. If you would rather join me in the lecture tomorrow, let me know so I can have a set time because I'm aware you're coming in. Okay. Other than that, y'all have a nice evening. Okay, so I'll end right here.